Hello, my name is Alicia, and today we're going to be going over Red Hat OpenShift AI. We will first go over everything on the OpenShift AI console, as well as going over an example of deploying a Llama model for inferencing on WebUI. Alright, let's get started. So this is the OpenShift AI console. This is our homepage where we can have a quick look at some of the features within OpenShift AI. At the top of our page, we can see some of our different projects that we have created within our cluster. Under that, we have some descriptions on how we can use OpenShift AI to work with AI and ML models. For example, we can organize our applications, connections, and storage. We can also train and create models using workbenches, as well as deploying them. If you scroll further down, we have some learning resources and documentation that can get you started. Under that, we have some buttons that can go straight into editing settings like managing your notebook images, serving runtimes, as well as cluster settings and user management configurations. There are more settings that you can configure if you click the drop-down menu for settings on the bottom of this left sidebar. Going back to the top of this sidebar, when you click Data Science Projects, you can get an in-depth list of all of the projects that you have within your cluster. Clicking the Models drop-down menu and then clicking Model Deployments will allow you to see all of the model deployments within the cluster and check on their health and performance. Under the Applications drop-down menu, we can see what we have currently enabled, as well as explore what we have available. The tools and applications that we have available are all things that you can use for parts of the data science lifecycle. For example, when starting the data collection and cleaning process, we can use Pachyderm to build pipelines to automate the flow of data from various sources, start the cleaning process, and also do data versioning and lineage tracking. In the next part of the cycle, we can start exploring the data and developing the models. We can use Elasticsearch on large and unstructured data sets in order to search through the data, as well as Starburst in order to do SQL queries on distributed data sets. Jupyter is used to create notebooks that act as a data scientist's Swiss Army knife. These notebooks can be used as a flexible and lightweight tool to visualize data, test and develop models, as well as conducting exploratory data analyses. Once we are ready to train and deploy our models, we can use Intel's One API toolkit in order to optimize machine learning workloads on Intel hardware. IBM's Watson X has a portfolio of enterprise-grade AI products to accelerate the model development process with pre-built workflows that can be customized for your specific use case. Lastly, we have a set of microservices and tools to optimize inference serving with both NVIDIA as well as Intel hardware, with NVIDIA NIM as well as OpenVINO. Moving back to the left sidebar, we can get a whole catalog of resources available for these supported applications that we just went over if you click Resources. Now let's go into our Demos project view. We can find this by clicking into the Data Science Projects tab and then selecting the specific project that we're using today, and then you'll be in the Overview section, where we can see everything at this top set of tabs at a glance. We can see our active workbenches, our deployed models, as well as our failed ones, and some more project configurations. Going back up, we can click into workbenches and make a workbench, which is a contained area where you can work with models, pipelines, and storages within your preferred IDE. Clicking into models, we can see what models we have deployed within this specific project and go in depth on their configurations when clicking this drop-down menu. Going into the Cluster Storage tab, we can connect this project to a persistent volume, one common example being an AWS S3 storage bucket. We can also connect our project to other external sources that aren't on our cluster under this Connections tab. For example, we have a connection to a quantized Llama model car that we'll be using for our demo today. This model car is a container image pulled from Quay.io that's packaged with all the necessary dependencies, runtime components, and things that are needed to run our Llama model. Lastly, for these top set of tabs, we can edit permissions for users and groups that are in this project, and also some extra settings that we can play with. Alright, now that we've gone over everything on the dashboard, we can get started with our demo of deploying a Llama model for inferencing. Because we're using VLLM for our inference serving, we have to check that we have a GPU provisioned and ready for use. To do that, we have to go back into the OpenShift console, and then on this left tabs, you can drop down the menu for compute, select nodes, and you can filter roles to see all of your GPU workers on your cluster. Going into that specific name section, if you go here and select pods from this top set of tabs, you can search for the NVIDIA drivers. As you can see, the NVIDIA driver daemon set is running and ready for use. Once you've confirmed that, you can go back into the OpenShift AI tab, and then we can now set up our connections to our Llama 3.2 3D model car. We can create a new connection by going back into your project view and selecting connections from these top set of tabs. And then we can click the blue Create Connection button right here on the right. As you can see, we currently have 3 supported connection types. The OCI compliant registry, which stands for Open Container Initiative, which you would use if you had a proprietary image that may require authentication and compliance to the OCI. Next, we have S3 compatible object storage and URI, where you can paste a link to access whatever resource you need to connect this project. If you select the OCI compliant registry, you would have to give it a name, drag and drop your secret authentication details, as well as specify the registry host. If you select an S3 compatible object storage, you would have to create that within the OpenShift console. One way you could do this demo utilizing this connection type is to upload a min.io YAML file to create a pod where you can run all of your model files on a web console in order to obtain all of the keys that are needed to create this connection. Since we're using a publicly available image off of Quay, which is an OCI compliant registry, we don't need any authentication. So we can just use the URI connection, where you just have to put a name and also the link to the model car image. Once you have that created, we can go back to the Models tab and select the Deploy Models button. Now we can give our deployment a name, and since we're using VLLM, we have to select the VLLM NVIDIA GPU serving runtime, as well as selecting the standard development mode. This is so that we don't have to set up any routes or ingresses for external access. With standard development mode, it will automatically be set up for us, but advanced deployment gives you more granular control over the networking, scaling, and resource allocation. Now, let's give our server a medium size. Then we can select the GPU that we just provisioned in this Accelerator tab. And for this example, we'll allow the model to be available through an external route as well as require a token authentication for security purposes. Lastly, we can just select the proper connection that we just established and add in extra configuration parameters. In this demo, we don't need to add any new arguments, and we can just select Deploy. Once we select Deploy and wait for the service to come up, we can check on the status by clicking this button right here. As you can see, it is available and loaded. If there are any issues, it will be displayed on this pop-up menu. We can test our deployment in the OpenShift console to see if the model can talk to itself within the pod. We can also check the external endpoint at this point as well. We just need to obtain our internal and external endpoint details, where we can click the blue link right here. And we also need our token for authentication. To get this token, click on this drop-down arrow on the left side of the model deployment name, and we can copy it by clicking the copy button at the end of the token at the bottom right of the screen. Now let's move to the OpenShift console again to check if the inference server is running internally. Now that we have all of that information, we can go into the OpenShift console in order to check if everything is running smoothly. Once we're here, we can go on the left side and click the Workloads drop-down menu and then the Pods button right under it. From here, we get to see all of the pods that are running within our project. Now we can see that our Llama predictor is running and ready. Going into this specific pod, we can click into this link and then select the Terminal tab from this top set of tabs. Now we can send in a curl request to see if the inference server can talk back to us. Since VLM uses OpenAI's API, you can go on their documentation to see more details. But for this example, I have one ready to be copied and pasted. As you can see, you have to make it a JSON content type, and then we have our local ingress route, as well as indicating that we want it to be a multi-turn chat by making it chat/completions. Now we have all the messages that are in this multi-turn chat. We have the specific model name, as well as our system prompt, you're a helpful assistant, our first response, which is hello, and then the model's response back to hello, and now we're going to ask it to complete our question, which is what is 2 plus 2? As you can see, it took that really quickly, and it responded the answer to 2 plus 2 equals 4. It's important to check that things are working at this point because sometimes the pod can be up and running, but this curl response would not work. In order to check that the external endpoint is working, I'm currently in my local computer's terminal. Firstly, you have to create an environment variable with your token. As you can see, I've done it up here. Now, we can edit our curl requests according to OpenAI's API format by adding in a header with our authorization details. You also have to change the external root right here. As you can see, it seems like everything is working perfectly. Now to deploy this with WebUI, I'll be using this open source repository as a template. We just have to edit this Helm chart with our specific configurations. To do this, you'll need to edit the values.yaml file and add our external endpoint and the token in this part of the file. You can add any other configurations as listed here. Now, you can use Helm commands to install OpenWebUI and launch it in OpenShift. Going back into my terminal, I have already pulled this repository and CD'd to it. I have OC and Helm installed in my command line, and I've logged in with my token to access. As you can see, I've edited the values file, and now we can just do Helm install OpenWebUI. As you can see, it was deployed, and we can use this specific command to get the specific URL. Clicking into it, we can see that we have a clean web interface up and running rather than having to painstakingly type out everything for a curl command. All right, there you have it. That's one of the ways that you could deploy and interact with the language model using Red Hat OpenShift AI. This is one of the many features and applications that Red Hat OpenShift AI can offer for your data science project.